Hello, and welcome to our practical investigation of IV characteristics of circuit components. In our recent lessons, we've laid the foundation for understanding electrical circuits. We've talked about current, which is the flow of electric charge. We have also discussed voltage, which is the potential difference that drives that flow. And we have learned about resistance, which is the opposition to the flow of current. We've also explored Ohm's law, which states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points, provided the temperature remains constant. This relationship is given by the equation R equals V divided by I, where R is resistance, V is voltage, and I is current. Today, we're going to build on this foundational knowledge by investigating the IV characteristics of different electrical components. This practical will involve measuring the current through and the voltage across components like resistors, semiconductor diodes, and filament lamps, and then plotting this data on a graph. By doing so, you'll gain a deeper understanding of how these components behave in a circuit. Before we get started, let's briefly outline the importance of this practical. Firstly, different components such as resistors, semiconductor diodes, and filament bulbs exhibit unique IV characteristics. Knowing these behaviours enables engineers and technicians to choose the right components for specific purposes. For example, semiconductor diodes with their nonlinear IV characteristics are essential in rectifying circuits that convert alternating current AC to direct current DC. Moreover, having a practical understanding can help in troubleshooting and diagnosing electrical issues. If a component behaves unexpectedly, understanding its IV characteristic can guide you in pinpointing faults or ensuring proper operation within broader electronic systems. Secondly, modern electronics, such as smartphones and computers, rely on components that operate under precise electrical conditions. Understanding these conditions through IV characteristics allows for improved design, energy efficiency, and performance optimization. Device manufacturers use this understanding to enhance battery life, minimize heat generation, and improve the reliability of electronic products. In this way, this experiment forms a crucial bridge between textbook principles and real-world applications, equipping us with the skills and insights necessary for both academic success and practical innovation. Now, let's dive into the practical and explore these fascinating concepts in action. Let's start by gathering our materials. Sam, what do we need?
So for this practical, we need a power supply, an ammeter, a voltmeter, fixed resistors, a diode, a filament lamp, a variable resistor, and finally, a lab book to record our results.
Once we have gathered our materials, we begin by setting up our first circuit, which uses a fixed resistor. Here is a diagram of our first circuit. Ensure to connect the ammeter's positive connection to the positive terminal of the battery supply. Attach the other terminal of the ammeter to one end of the fixed resistor. This ensures that the current flowing through the power supply first passes through the ammeter before reaching the resistor. Next, set up the voltmeter such that it measures the potential difference across the fixed resistor. Connect the negative terminal of the voltmeter to a variable resistor. Finally, connect the negative variable resistor to the negative terminal of the power supply, completing the circuit. Ensuring that the positive terminal of the power supply is connected to the ammeter's positive connection, and the negative terminal of the power supply is connected to the variable resistor is crucial, as this will change later. Once you have carefully set up the circuit, double-check all connections to make sure they are secure, as any loose connections could affect our measurements. Now we turn on the power supply. As we can adjust the resistance using our variable resistor, we will start with the lowest resistance level. At this level, record the measurements given on the ammeter and the voltmeter, and record them carefully in your lab book. Gradually vary the voltage across the component by changing the resistance of the variable resistor. Check the appropriate voltage reading on the voltmeter. For each increment of voltage, take the corresponding recording of the current reading from the ammeter. We then repeat this process for a range of voltages up to 10 volts. Carefully record the results in your lab book. Next, we are going to swap the connections on the power supply. This means that the positive terminal on the power supply will now be connected to the variable resistor, and the negative terminal will be connected to the ammeter. This allows us to take negative readings for voltage and current on the ammeter and the voltmeter. Repeat the same process as before using the variable resistor to gradually alter the voltage, recording both the voltage and the corresponding current in our lab books. Our table will look something like this. Now, replace the fixed resistor with a filament bulb. Ensure that the filament bulb is placed in the same position, such that the voltmeter is connected around it and measures the voltage through this particular component. Begin with the positive power supply terminal connected to the ammeter and the negative terminal connected to the variable resistor. Repeat the same process as we did with the previous circuit, using the variable resistor to alter the voltage and the current and taking recordings of both. Once this is done, switch the connections at the power supply and repeat again, making sure to accurately record results in our lab book. Finally, replace the filament bulb with a diode. Repeat the process by turning the power supply on, adjusting the variable resistor, and recording the voltage and current as they change. Once done, switch the connections at the power supply and take the negative readings for the voltmeter and ammeter. Well done on completing the experiment. Now we can move on to the analysis of our results. You should have multiple recordings in your lab books of the voltages and currents in a circuit for a fixed resistor, a filament bulb, and a diode. Let's plot graphs from the data we collected. As usual, we'll put our independent variable potential difference on the x-axis and our dependent variable current on the y-axis. Beginning with the fixed resistor, we see the following shape. From this, we see the potential difference across a fixed resistor is directly proportional to the current flowing through it. This principle is known as Ohm's law, and this fixed resistor is considered an ohmic conductor. Next, let's plot the graph for the filament bulb. Immediately, we can see that potential difference is not directly proportional to current for a filament bulb. The explanation behind this is that as the potential difference increases, the temperature of the filament inside the bulb rises too. The higher temperature causes the ions in the filament to vibrate more, which makes it harder for electrons to pass through. As a result, there is greater resistance to current. Finally, let's see the graph of a semiconductor diode. Again, we can see that a semiconductor diode does not qualify as an ohmic resistor. We also see that a semiconductor only allows current to flow in one direction. If the potential difference is arranged to push current the wrong way, no current will flow as the resistance remains large. Once the potential difference is set up correctly, we see that semiconductor diodes have high resistance at low temperatures. However, at higher temperatures, the resistance decreases and the current flows. That concludes today's practical, where we investigated the IV characteristics of a resistor, a filament lamp, and a diode. We plotted current voltage graphs for each component, highlighting ohmic and non-ohmic behavior. Throughout the lesson, we also emphasized accurate reading and recording of key data points, and practiced plotting and interpreting IV graphs. These are essential skills for analyzing electronic components. Moving forward, remember the importance of understanding the distinctive characteristics of different components. Moreover, developing precise measurement and analytical skills will aid your comprehension of more complex electrical topics and will be invaluable in both exam settings and real-world applications.